Now let's look at another situation related still to nucleation growth model, except now the growth becomes diffusional controlled. Diffusional controlled. Okay. For diffusion controlled three-dimensional spherical growth scenario for nucleation growth, we said diffusion controlled, so typically the linear dimension of the precipitate would follow so-called parabolic relationship, which is essentially the thickness for or the linear dimension for the precipitate is proportional to the square root of dt. Again, d would be diffusion constant, t would be time. The thickness would be linearly proportional to square root of dt. Of course, there may be other factors in front, but it's linearly proportional to square root of dt. And if we can write x equals to a constant times t to the power of zero point 0.5 or square root of t. Okay, this relationship links the precipitate thickness, layer thickness, and the time t. Okay, which we call parabolic relationship. And if we say the growth is three-dimensional spherical growth, and the growth is accompanied with constant nucleation rate, which means over time per unit volume, untransferred volume per unit time, the number of new nucleus formed is a constant of a constant value. And then also at the beginning, when t is 0, there is no nuclei. There's no nuclei. With all those in mind, then the extended volume again includes both the real precipitate and the so-called phantom precipitate, those that nuclei that occur within a transformed volume, which when you say random, it would happen, but in reality, it will not happen because that portion has already transformed. So the extended volume, in this case, of the regional phase would be Vext for extended volume would be integration of individual volume formed at a different time tau, V tau times dn. Okay, and then we write V tau would be 4 over 3 pi r radius to the power of 3. And what is radius? Radius would be linear growth rate times t minus tau to the power of 0.5. Okay, why t minus tau? Because that's the time left for a nucleus that is formed at time tau. How much time does it have for it to grow? And the growth follows parabolic relationship, which means x is a constant u times square root of t. So constant times square root of t. And then the total radius to the power 3, that gives you the volume of a sphere. Okay, this gives us the total volume for a individual nucleus formed at time tau, and then times n, how many of that thing, times d tau. Okay, of course, this is for the case for extended volume, which include overlapping. And then let's put that the constant in front of the integration sign. 4 over 3 we put it in the front, pi we keep it in the front, n is a constant, we keep it in the front, and the u 0.5, 3 times together 1.5, so u we would have u to the power of 1.5 or 3 over 2, also put that in front. And within the integration symbol, that is just the t minus tau to the power of 3 over 2. And integration with respect to time tau. Of course, tau is from 0, from the very beginning, to t at the time that we are interested. Okay? And then the extended fraction of transformation would be a constant times t to the power of 2.5. That is after the integration of this term. Now it's t to the power of 1.5, but after integration it becomes 2.5. So the fraction of conversion for extended volume, which include both real and phantom, would be a constant times t to the power of 2.5. Okay, then using the same principle, the real fraction of conversion f would be 1 minus exponential term minus extended fraction of conversion. And the extended fraction of conversion, from here you can plug it into this equation. Therefore, we would have the real fraction of conversion is 1 minus exponential term. Okay, this f term would be a constant chi prime t to the power of 2.5, which don't forget the negative sign in front. And for this equation, we can get the extent of conversion for a given time t. Okay, if we know the constant of k prime. If we do not know, but you actually measured in experiment, then we can take natural log of 1 minus f, a natural log of the exponential term, and move the negative sign to the left side. This is what we are going to have. Time t versus fraction of conversion. And when t goes toward infinity, when t goes towards infinity, the fraction would go towards 1, and within the bracket it goes towards positive close to 0, and take natural log, that's negative infinity, but there's another negative sign, so become positive infinity. So left side and right side, they become consistent. Okay, and for this we can do one more manipulation. Take the power of 1 over 2.5, then we would have the equation be proportional to kT, and that is often the case for kinetics, relates to a constant times t. Again, k would be the reaction constant, t would be time, f would be the real fraction of conversion. For this case, so-called nucleation growth, it does form nuclei and it grow, and it's constant nucleation rate, not site saturation. But in this case, the growth would be diffusional control, which means the layer thickness follows parabolic relationship. Our x squared equals dt times the constant. Our x is equals to a constant times t to the power of 0.5. Okay,